Okay, so now that we had this review of the former concepts and we have set our new goals for this tutorial, let's step in and see the use case of this tutorial, the second part, which is based on the first tutorial and is allocated in Madrid, where we will have several sensors of different types with different functionalities, and we will see how and what we need to describe all these sensors, their information, and how to describe how they are located in this case in the city of Madrid. So starting from the sensors, for this use case, we will have three different types of sensors. We will have lampposts, which are the icon of a regular lamppost. In this case, we will have 6 of them. We will have 2 photometers, which are represented by the icon of the light bulb with the lightning. And we will have 2 smart lampposts, which are a mixture of lamppost and photometer. So these sensors have all the functionalities of a lamppost and also photometers, and they are described with described with the icon of the lamppost and the light bulb with the lightning in the bottom. So having all these sensors, now what we will need to do is identify their informational requirements and see how to combine them with other concepts. In this case, the other concepts will be a set of streets from Madrid. These 4 streets, in this case, Tudescos, Fuencarral, Gran Via, and Montero, which are 4 of the most well-known streets in Madrid. And these streets will be related to a set of neighborhoods, districts. In this case, Madrid Center, Universidad, Embajadores, Cortes, Justicia, Palacio, and the most well-known Sol. And notice that in this case, not all the districts have data about their streets, and therefore they do not have data about their sensors. This is important because we will need to describe the data that we want to exist in speaking in virtual terms. So in this case, in Madrid Center, even if we have a lamppost or we have a photometer or even a smart lamppost, if we do not describe that sensor or we do not describe the street or well, in this case, we have the district, and we do not relate the sensor with the street and the district, at the virtual level, they will not exist. So this is really important to perform these operations. And finally, when we have the districts, we will need to relate them with the city. And in this case is Madrid. And for this use case, we only have Madrid, but in another bigger or larger use case, we could have more sensor, even more types of sensors, more streets, more districts, and of course, more cities. But we will keep it smaller for this use case. Now, once we have the types or the entities we want to describe using RDF and semantic descriptors, in a practical use case, what we need to do is to somehow elicitate a set of informational requirements. This means what we want to express, what data we need to express using RDF and using ontologies, and that we will need afterwards to query, or that will be useful somehow for someone that will need to interact with the sensors or the city. And for this use case, the lamppost will have a manufacturer, they will report measured properties, they will have a revision date, and they will have information about the light that they project and its characteristics. We will see later more in detail example. For the photometer, something similar, we will have the measured properties and the revision date. And then for the smart lamppost, we will have a combination of the informational requirements of the lamppost and the photometers. And finally, for the city, we will have a very simple model, simple informational requirements. In this case, only the name of the street and the geographical location. For the neighborhood, something similar, this district, and of course for the city. So for all these geographical elements, we will have basically the latitude, longitude, and name when it will apply, and also the relationship between these concepts, whether they are contained one into another. Then when we have done this elicitation, we will need also to see if we can somehow relate or enhance the relation of, in this case, the sensor and the streets. And for this goal, either the lamppost, the photometer, and the smart lamppost will have assigned a street, and also they will have a latitude and a longitude. This is interesting because if we capture this informational requirement and we have keeping an eye on the future, we will be able to know, if we think beforehand on the type of queries we want to perform, we will be able to know which information we need to capture in order to perform these queries. And in this case, keeping an eye on the future queries, and these were also showed in the previous tutorial, if we keep latitude and longitude, we will be able to express queries like, tell me the lampposts that are nearby to me, providing, of course, my position in latitude and longitude. Or having the location, the assignation to the street, we will be able to say, tell me all the lampposts that are nearby this street. So these informational requirements, as you can see, are really important because they somehow capture the type of interaction we will be able to have with these devices afterwards. Once we have these informational requirements captured, okay, we will be needing of, or we will need to perform somehow research on the type of ontologies that will allow us to express that information. But before going into that, let me show you an example of the informational requirements captured for this use case. So as I told you before, smart lamppost in this case is a mixture of lampposts, regular lamppost, and photometer. And here you can see the informational requirements, an example, capture for the smart lamppost. Notice that here we are not yet talking about RDF or ontologies. This is just the type of information we would like to offer for this sensor. So in this case, we say smart lamppost, and notice that smart lamppost has already a connotation. It's a type located at gran via. So in this case, we can see that we are entailing that the sensor is somehow located somewhere, in this case, gran via, which is a street, and the lamppost has this position, the latitude and the longitude. Then it has a manufacturer and a last revision date. And here you can see that it measures the luminance, illuminescence, and the photophorescence. And finally, it projects a light without flash that has an angle of 180 degrees, and the color of the light is warm white. So here you have an example of the kind of data that a human somehow would like to have for querying this, or just to checking to retrieve the data of this smart lamppost. Now the question is, we have the information that we want to express, and this is an example, how we express that data in the semantic descriptors in order to register this sensor in the CSC. Once we have these informational requirements clear, and for instance, in this example, we need to choose which kind of ontologies we are going to use in order to express the RDF data. But before going into that, notice that once we have all these informational requirements, and just to double check them, we should try to perform a list of semantic queries expressed in Sparkle that we know beforehand. That would be the optimal scenario, or in worst case scenario, we think users could want to query the data, and in this case we should try to elicitate those list of queries in order to double check that the semantics captured in the informational requirements are correct, and we do not need further adding further semantics there. And in this case, you can see that the list of queries is the same from the first tutorial. Just to give you some highlights, Some interesting queries could be the number 3, find sensor on the Sol neighborhood from Madrid that measures illuminance. So for instance, check here for this query, we need the semantics to express sensor. Sensor is something generic. We are not talking here about lamppost or photometer or smart lamppost. This is just sensor. And sensor has a semantic associated. It means any device. So in this case, it will mean any sensor. So when I ask for this, I should be able to retrieve, regardless the specific type of the sensor, all the devices. Then Sol neighborhood. So in this case, we are specifying that we will have neighborhoods, and they will have a name in this case. And from Madrid, and in this case, they are located in Madrid, that measure illuminance. So it means that the sensors should somehow report the measured properties. So with this query, we can check that actually we are keeping track of all the semantics we will need in this list of informational requirements we performed before. Okay, so we should try to do this dual task for all the queries and double check all the informational requirements previously elicited. After this task, if we needed to add more informational requirements, we can do so. Otherwise, we need to move forward and start picking which ontologies we are going to use. In this case, for our use case, we could use, of course, one or more ontologies, but the key point here is to choose ontologies that will allow us to express concepts like lamppost, photometers, streets, and so on, and all the properties related to them. Like before, I mentioned the latitude, longitude, or the manufacturer, or the revision date. Also, the ontologies we need to choose must be standards. This is really important. If we develop our own ontologies, it is unlikely that other people will reuse our ontology. And even if there are mechanisms to perform interoperability among ontologies, and we will get into that point right now, it will be hard that people choose to perform the task associated to enable the interoperability with our ontology, since it's an unknown ontology and used for a very narrow scope. Instead, if we choose an ontology, one or more that are standards, first of all, we will have a huge community that will back up the formality and the validity of that ontology. And also, it is very likely that someone will have already developed the different the alignments, they are called, between the ontologies if they are standards. This happens, for instance, between SAREF and oneM2M. So and this is the third point, if we choose more than one ontology, they should be somehow related. And there are two ways of relating two ontologies. The first one is extending one ontology. So basically taking the, let's call it the core ontology, and developing domain-specific modules and somehow relating the concepts. Or the other option is using alignments. The alignments are a kind of extension, but basically enable the interoperability among the different ontologies, and they hold somehow, the alignments are definition of somehow restrictions over the concepts and properties of the ontologies, and basically they state the equivalence between concepts and properties. So in either cases, if we use more than one ontology, we need to A, use the extension mechanisms, or B, using the alignments. For instance, in SAREF, we have a core element, a core ontology, and then we have a lot of different domain-specific modules. Those modules are already extending the core ontology. So if we want to use SAREF, we do not need to extend anything because SAREF is already meant to work in that way. So we will have the core ontology that I will show you in a few slides, and then we will have different specific domains ready to use. Just you to know that the SAREF initiative started in 2013. It was promoted by the AC and ETSI, TC Smart M2M, and the development of the SAREF ontology and its extension. It's published in the ETSI portal, and it's part of the ETSI standard. And you have there the URI or the URL, sorry, to the portal. And if you navigate there, you will see that you have the core ontology and then a list of the extensions. So in this case, SAREF is already a standard, and it's already meant to work with domain-specific modules ready to use. So in this case, what to do, it's easy. We just need to check which modules we need for this use case. And in this use case, we will need some concepts from the extension of smart city, because we will have cities, even if it's just one, we will have districts, streets, and so on. And we will choose as well the environment extension, because it is meant for expressing data specifically for lamppost and characteristics of lamppost. So it's the suitable choice in this case. Now, if we want, now that we know we want to use these ontologies, we need to go, in this case, to the, I picked the diagram, but the correct choice or the correct movement would be to go to the portal and see the model they report. So here you have a capture of the core SAREF ontology. And here what we need to do is to check which entities are expressed already in the ontologies, and which of them we will need to use in our data, because then we will need to write the semantic descriptor, following this model. And in this case, you can see here in the center, we have the concept SAREF device that measures properties and also that has a state. And well, this is directly related with the informational requirements we were discussing before. If you recall, also with the query, I choose to highlight the informational requirements that we may need to add, and in this case we have SAREF device. So for the query that state, find any sensor that had some restriction, in this case we have the SAREF device. So we could convey that query using the SAREF device. Another informational requirement we had, and it repeated, was the measured properties. And in this case, we see that the core SAREF had that. And for the state, we will see afterwards. Now, once we have that, which are very abstract concepts, we will need to dig into the detail of those concepts. And for this, we will use SAREF for city, which is the extension for cities. As you can see here, the SAREF for city extension is extending the core ontology, and you can check this if you notice in the center of the ontology we have the SAREF device. So this ontology revolves around the SAREF device and extends it. Actually, if you can check the right circle on the bottom, you will see that the device is somehow related with the geosparkle ontology feature, and is related, and this entity has also a subclass: city, country, district, neighborhood, and so on. And if you recall, another thing we need to express were the latitude, longitude, and in general geospatial information. So if we pick in this ontology as marked in the top red circle, if we pick this ontology, we already have all this information, all the geospatial information, because the SAREF for city extension is not only extending the SAREF core ontology, but is also relating this ontology with the geosparkle ontology, which is also a standard. So this is the right choice for these informational requirements, because we are covering two sides of the informational requirements. On the one hand, all the information about the city, and on the other hand, all the information about the geospatial, like the latitude, longitude, and or maybe the contain, the relationship contain, in order to say that a lamppost is contained, for instance, in a street. Now, this is great for the city, but as you can notice, it's not usable for the specific case of the lamppost and so on, and the sensor. So what can we do in this case? Well, in this case, we are going to rely as well on the SAREF for ENVI, the environment extension of SAREF. And you can see here again, in the center of the ontology, we have the device, which is the SAREF device. And this ontology is extending this device with the lamppost concept. You can see it in the bottom. And this ontology is also offering data about the light projected by this lamppost. And you can also relate that all these concepts are again linked to the spatial thing concept from the GeoSparkle ontology. So basically, this is not the whole diagram of the ontology. It's just a capture, but you can see how the SAREF core ontology is the central pillar around which the rest of the ontologies, the extensions of SAREF are gathered, and they add information, or they even linked the core concepts of SAREF with other ontologies, in this case, like the GeoSparkle. So with these choices, we cover all the information about the lamppost and the light that they project, the geospatial information, the properties, and the city. And in this case, you have an example here. This is a very rough aggregation of information because it's not entirely true. So you can see in the first red square that all the information inside belongs to the SAREF for ENVI ontology, and the one on the bottom to the SAREF for city. In this case, the SAREF for city has not much weight because we are talking about a lamppost, which belongs to the SAREF for ENVI ontology. But notice that, for instance, the geolatitude, geolongitude, geo has geometry, all these concepts, they do not actually belong to the SAREF for ENVI ontology, but to the GeoSparkle. But in this case, since they were described in the SAREF for ENVI, and in the diagram I showed you before, we gathered them in that box. But if you recall, they were also mentioned in the SAREF for city. Okay. In this case, since they do not appear related to a concept from the SAREF for city, we just left them in the SAREF for ENVI box. Anyway, you can see here now with this piece of RDF, how using the SAREF ontology, the SAREF for ENVI, and the SAREF for city, we are expressing all the informational requirements we mentioned before. In this case, the type, which is the lamppost, the manufacturer, the geoposition, the revision date, and the information about the light, that is a light, has no flash, has an angle that is 180, and has a color that is warm white. And this lamppost is located in Fuencarral. So you have here a piece of RDF. Now, as Bob mentioned before, we want to align SAREF with the oneM2M ontology in order to enrich our semantic descriptors and have new informational, well, this will entail that we will have new informational requirements, but will also entail that we will be able to perform new operations and describe new semantic queries like the ones Bob mentioned before. In this case, what the oneM2M ontology allow us to do? Well, in this case, describing how to interact with a CSC in order to perform actions over the sensor described, like the one I showed you before, with the SAREF and its extensions. And this is related with the example that Bob mentioned before, that was how to turn on the lights or how to perform a switch on or switch off operation. Now, this is in the oneM2M ontology. The informational, the entities, the properties, all the capabilities to express these informational requirements are located there and not in SAREF. So how we use both of the ontologies, how we link them in order to use both of them regardless, which is basically semantic interoperability. How we can express a query in terms of oneM2M or in terms of SAREF, and the Sparkle processor will be able to understand any of them. Well, in this case, we will need to use the well-known alignments, which are part of the ontologies and also the OWL standard, which allow us to sue somehow the different ontologies using equivalent terms among them. But at the same time, they allow us to keep some unique terms. So just to give you an example, because this is a very abstract thing, in SAREF, we have the SAREF device, and in oneM2M, we have a oneM2M device. Now, the SAREF device will have some properties like the name, and the oneM2M device will have as well some properties like the name. But then the oneM2M device will have some unique properties that do not exist in SAREF. So we want to create the alignments between the two types to say that the SAREF device and the oneM2M device are equivalent, so they are the same, and also that the property name are the same. Now, what about the unique property of the SAREF device? Well, we want to keep that because there is no term in SAREF that has the same semantic connotation. So we will have that as a unique. Once we have created these alignments, we will be able to express Sparkle queries specifying that we want to retrieve a SAREF device. And when we will send that query, even if the semantic descriptor mentioned that the device was a oneM2M device, we will get back the results of that semantic descriptor. And the same happened on the other way around. You noticed before I show you the example of the semantic descriptor of a lamppost expressed with the SAREF for envy and the SAREF for city. If we perform these alignments with a oneM2M device, I potentially could write a Sparkle query expressed uniquely with oneM2M terms and retrieve the exact same results that they could be retrieved if I wrote the same query using the SAREF terms. So the question is how we perform these alignments. Well, in this case, it's really easy. It's just a two-step task. The problem is that we need to repeat this a lot of times. So first thing we need to do is to find in the two ontologies we want to align, in this case, SAREF and oneM2M, the entities, the classes declared in all that we want to align. And we want to declare that they are the same. So as mentioned in the previous example, here we have the SAREF core device. We choose this class because, as I mentioned before, all the extensions revolve around this entity. And in this case, you see here the OWL declaration. So this is the ontology, how in the ontology it is said that this is a class. And below we have the same, but for the oneM2M ontology. And in this case, we can see that this oneM2M device, it's also a subclass of the oneM2M thing. Okay, so now that we have identified these two classes and we want to say that they are the same, we need to perform an alignment. This alignment looks like the following one. So you can see in the first blue box that we say SAREF etc org/core/device RDFS subclass of the oneM2M device. So using this statement, we need to create a new OWL file and perform all these declarations among the different classes. And after that, if we load this file into our triple store and we perform a query specifying find any SAREF device, we will be transparently retrieving any oneM2M device. And if we perform the same query, but instead of saying retrieve any SAREF device, any oneM2M device, we will retrieve transparently any SAREF device. Now, similarly for the properties instead of the types, if we want to say that something is equivalent to one property is equivalent to another, we need to write the statement in the second blue box. So in this case, we will say that SAREF etc.org core has state. So basically, SAREF has state. It's an RDF subproperty of has thing property. So specifying this, it will happen the same as the type. We will get returns transparently, regardless if we say has state or has thing property. And this lead us to actually one of the goals that Bob was mentioning before. that was expressing the oneM2M commands. So if we had the previous semantic descriptors and we want to enrich them with the terms from the oneM2M ontology to specify the different commands that those devices have, what we need to do is to take our semantic descriptor and perform the alignments and then enrich this descriptor. And in this case, you have an example of how to enrich a photometer with oneM2M terms. Just recall, we have performed this alignment among the different ontologies, and therefore we will be able to transparently query all this. We will see the query afterwards. So in this case, you can see that we say that a photometer has a state. In this case, has two states. Each state has a URI. The first one is the photometer sensor 1 measurement, and the second is photometer sensor 1 status. And then we have another property that is the data type. And finally, we have the oneM2M method that in both cases is retrieved. Notice that in the second state, we also have an additional property that is the data restriction. And in this case, it will report that the photometer says if currently is day, night, dawn, or dusk. So once we have enriched the semantic descriptor, we have created the alignments, and we have loaded everything in our triple store, we will be able to perform this transparent query using the terms from both ontologies transparently. And in this case, you have two equivalent queries. If you check the first one, both are reporting the sensor, a property of the property ID of the sensor, the type of that property, the URI, where we need to perform the invocation, and the method to do so, which is basically the information that Bob asked in the example he showed before. And you can see that both queries return the same, but they are expressed in different terms. So the first one specifies a oneM2M device that has a think property, and this property has a type, a target URI, and a oneM2M method. If we check the second query, instead of a oneM2M device, it is asking for a SAREF device that has a state. Since we said that the oneM2M device and the SAREF device were equivalent, and the has state and the has think property were the same, the results will be for both queries the same. Now notice that here in the second query, we could not specify an equivalent term for the oneM2M target URI and oneM2M method. This is fine, this is normal, because ontologies are developed for different goals, and when we align them, we cannot always perform alignments for all the terms or all the types. So this is fine. These are unique terms from oneM2M, and if we want to express a query that must rely on these terms, unfortunately, if we use SAREF, we will need also to invoke these terms. But this is okay, and this is the way in which Sparkle works. So it's normal to have terms from different ontologies in the same query. Now, how about some sample discovery queries with these new extensions? Well, these queries could not be done in the previous tutorial because we didn't extend the ontology, we didn't align the ontology of SAREF with the oneM2M. But now that we did, we could perform queries like how to turn on a lamppost, can a lamppost be switched off, or how to retrieve the value measured by a photometer. So notice that these queries become really interesting and are really have a really rich information, because for a new user, will tell and will specify how to interact with this sensor that was previously registered in the CSC. And now, regarding how to do so, Bob will explain how to perform the different operations that we need to register these semantic descriptors once they are created.